The second fundamental theorem of calculus is now getting to the gist of what this whole thing is really about. And the idea is that we first can really treat the integral from a to b of f of x dx as a number. This is a number. This is an area beneath a curve in the x-axis. So I would see this as a definite integral as a number. But what I can actually do is change this so that my lower limit is still a, but my upper limit is the input variable. And we're going to change the f of t dt to just be f as a function of t. And I'm actually going to define a new function, f of x, big F of x, as this type of function. And this is a new way of thinking about things. I'm not going to lie about this. You're going to have to spend some time thinking that what is happening is that this right here, this upper limit, is the input of the function. So what this kind of is here is this is a definite integral as a function of x. And the word for this, the thing that we use, is called an accumulation function. This is an accumulation function. It accumulates area. So I want to start with just an example of this. F of x is equal to the integral from 0 to x of the cosine of t dt. And we're going to t-chart this, and I'm going to actually do a couple of these where I do x and f of x, and we're going to evaluate this at 0, at pi over 6, at pi over 4, at pi over 3, and at pi over 2. So let's check this out. So if I plug this in for 0, what I get is the integral from 0 to 0 of cosine of t dt. Well, that's just 0. And visually, I want to create an image of this because the cosine graph looks like this. And if I'm doing the integral from 0 to 0, that's just this piece here. So that's nothing. But then we can move on, and I can say, all right, well, what is the integral from 0 to pi over 6 of the cosine of t dt? And on this graph, pi over 6 would occur somewhere in here. So that means this area right there. And that area would be representational of big F of pi over 6. And if I evaluate the integral of the cosine of t dt, well, the integral of cosine is negative sine. So evaluated from 0 to pi over 6, this is really just equal to the negative sine. Positive sine. The positive sine of pi over 6. And the sine of pi over 6 is 1/2. So this area is 1/2. Then we proceed outwards a little bit more, and I do pi over 4 would be right here. So this area, we're now accumulating even more area. And that area would be representational of big F of pi over 4. And that would be the integral from 0 to pi over 4 of the sine of t dt. Or the cosine of t. And we saw from below that that is just the sine of pi over 4, and the sine of pi over 4 is root 2 over 2. Sorry, this would be 1/2. And then we can keep going. So let's do the pi over 3 would be just a little bit more. So if I'm going to go just a little bit more, I'm now accumulating even more area. This was pi over 4. So now let's get f of pi over 3. And I get the integral from 0 to pi over 3 of the cosine of t dt. And that is root 3 over 2. And finally, for my set that I did, I can do the entire top region, this whole thing here. This would be big F of pi over 2, which is the integral from 0 to pi over 2, or the sine of the cosine of t dt. and that is equal to 1/2. So as I increased my x, what I actually did was it's like I'm increasing the amount of area that I'm taking. I'm accumulating area. Accumulation means to gather, and an accumulation function is a function where one of your limits is a variable. I'm going to kind of go back and characterize this a little bit more, where f of x is equal to the integral from 0 to x of f of t dt is an accumulation function. Where the input is, in this case, the upper limit. It can actually be either limit, or both. That's kind of a different thing. But I want you to think about it as a function that gathers area. We're going to spend a lot of time in the next couple of days on accumulation functions. So the point of this is that the theorem, which is called the second fundamental theorem of calculus, the second fundamental theorem of calculus. So the first fundamental theorem that we did before defines that the integral from a to b of f of x dx is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. That's the first one. The second fundamental theorem of calculus is even more fundamental in a way. And what it's saying is that if I have this f of t, say given big F of x is equal to the integral from 0 to x, and I'm not even going to do 0 to x, I'm actually going to just do a to x, some constant a. And I'll even replace that here because that's consistent with what we were doing up above. It doesn't necessarily need to be from 0. But given that f of x is equal to the integral from a to x of f of t dt, so f of x is an accumulation function. Given that, then the derivative of this, f prime of x, is equal to, okay, ready for this? What we're doing is we're going to take the derivative of an integral, which means we're going to do the true derivative of this integral. Now, the antiderivative of f of t by what we did up above is f of x, sorry, minus f of a. So let me kind of back up here a little bit. I'm going to try to prove this in a way that's going to make sense. This same thing is equal to f of x minus f of a. And I know that that sounds weird. This is the similar f of x here. So let's just kind of think about this as applying the first thing. And I'm going to erase that as well and get back to talking about the derivative. But what you have is you have the derivative of the integral, which means that the derivative of this would just be the derivative d dx of this f of x minus f of a. And the derivative of f of x is just f prime of x, which we kind of already know. And the derivative of f of a is 0. So this is just f of x minus 0. But f prime of x is just this f of x. This is the result I get. Okay. That is a more complicated way of saying something so stupidly simple. What it's saying is that the derivative of an integral is the function. This right here is the integral of f of t, so its derivative is just f of x. That's in essence what the second fundamental theorem says. It says that integration and differentiation are opposites. I know, it's so, we've kind of know this, but we know it because of this second fundamental theorem. Okay, second fundamental theorem is not one that you're actually going to use like that. So don't freak out if this didn't make sense here in the middle. All that I really want you to get at is that you have this function, this big f of x that's an integral, and its derivative is this little f of x inside. So In a way, what we are kind of getting at is that you have this sequence here where we have a function, then you have f prime of x, then you have f double prime of x. But if I go up above it, I have big F of x, which is equal to an integral from a to x of f of x, or f of t dt. I want to be able to go the other way. So this is going downwards, this is going upwards in the chain, and it's actually defining a little bit of what that integral means. So if I have a function, its integral is an accumulation of the area under its curve. We're going to do some examples of how to take a derivative of an accumulation function. So number one, I'm going to define f of x is equal to the integral from 5 to x of t cubed plus 5 under a radical dt. And I want you to find f prime of x, its derivative. Its derivative is exceedingly simple. Think about this chart I just drew right up above. I'm looking right here. So its derivative should be right here. And its derivative is simply f of x, this thing, right in here. Its derivative, I know this is going to seem almost too easy, is root x cubed plus 5. That's it. That's all that this is. F of x is equal to root x cubed plus 5. A couple of points about this. This 5 here didn't matter at all. Not at all. Because when I take the integral of this whole thing, and you can do, well, you don't know how to take this integral, but what I'm doing is I'm substituting 5 in as a lower limit, and then I'm taking its derivative, and its derivative is a derivative of a constant. That derivative of a constant, 0, that drops out. So let's get down to another one. Let's do the derivative, d dx, of the integral from pi over 2 to x of the cosine of t dt. And this is a derivative of an integral. Derivative, integral. What I get is the cosine of x. That's it. That's all that it is. Now, this is just an application of the second fundamental theorem, but this is the first application that we really need to focus on. Okay, another one. Derivative of an integral, pi over 2 to x cubed, cosine of t dt. This is going to be a little bit of a different case, just slightly different. I need to worry about something that we've referred to many times called chain rule. And to do chain rule, the process is I'm going to take this x cubed and substitute it. So I get the cosine of x cubed. But then I need to multiply it by the derivative of x cubed, which is 3x squared. Keep in mind that this is working this way because the lower limit is a constant. Its value is not changing. We will get to what happens when the lower limit is a variable. We're going to do that here in a minute. But let's do another practice of the derivative of the integral from negative 50 to x plus x squared of 5t minus 1 dt. Well, first step, let's just substitute this in. So I have 5 times x plus x squared minus 1. But then we're going to multiply that by the derivative of x plus x squared, which is 1 plus 2x. And I'm just going to do a little bit of a cleanup phase. 2x plus 1, 5x squared, plus 5x minus 1. Okay, next, we're going to do the derivative of an integral from negative x cubed to 1 of 2t minus 1 dt. So now I have the variable in the lower limit. And as you should be aware, I can pull a negative out and switch the lower limit and upper limit. So now I'm going from 1 to negative x cubed of 2t minus 1 dt. So I have negative d dx of 2 times negative x cubed minus 1. And again, I don't do anything with the lower limit. Oh, sorry, I don't have negative d dx. I'm actually just taking its derivative, so that's out there. But I have to multiply by the derivative of negative x cubed, which is a negative 3x squared. So the negative cancels, and I get 3x squared, negative 2x cubed minus 1. And I like to pull the leading negatives out to make this negative 3x squared, 2x cubed plus 1. Okay, next example. We're going to take the derivative of the integral from negative 2x to x cubed of 2t dt. This is the first example we've had of one where both the lower and the upper limits have functions in them. So this is also going to be a simple process once you do it. But I want to prove this once and then never again. We're going to take the derivative of, and I'm going to split this into two integrals. First one's going to be from negative 2x to 0 of 2t dt. And the second one is going to be from 0 to x cubed. And really, I don't need to use a 0. I can just use an a value. As long as that a is constant, it doesn't matter. So I'm proving what I'm doing by splitting this into two different integrals and then taking the first one and flipping it around so that this becomes the derivative of, well, let's switch the order about these. So I'm going to make this the integral from a to x cubed of 2t dt. And now I'm going to switch the order again, like I just said, of this one here. So it becomes minus the integral from a to negative 2x of 2t dt. Now I'm simply going to substitute the x cubed in, 2 times x cubed, but then times the derivative of x cubed, which is 3x squared, minus, then I'm going to substitute 2 times negative 2x, and then times the derivative of negative 2x, which is another negative 2. So cleaning all this up, I'm actually going to get 6x to the 5th minus 8x. And that's it. A far, far quicker way to think about this is that if you have the derivative of an integral where the lower limit and the upper limit are two different functions in terms of x, the way you're going to do it is you're going to take the derivative of the upper limit by chain rule, g prime of x, times, then you're going to substitute this in, f of g of x, minus, then you do the same thing with the lower limit, h prime of x times f of h of x. That will give you the derivative of some of these complex ones. So you're going to find a couple of homework examples that tend to do that, but really it's just going back to what happened here was the quicker way to think about this problem would have been to just say, all right, take this and substitute it. 2 times x cubed times the derivative of x cubed is 3x squared minus, then just take the 2x and substitute it. 2 times negative 2x, then times the derivative of negative 2x, which is another negative 2, and bam, you get the same thing that you would right down there. Okay, the next part of this, I want to talk about an AP problem. And I wouldn't normally do this, but I want to give you a sense of how this all ties together. And this is a free response question that actually appeared on an AP exam, and it's one that you can answer now. You actually have the capability to completely answer this. So for instance, this function is defined on the interval negative 5 to c, where c is greater than 0, and f of c is equal to 0, which means that that's an x-intercept. The graph of f is consists of 3 line segments and a quarter circle, with the center at negative 3, 0, and a radius of 2. Okay, and then it wants the average rate of change of f over the interval. This completely ties into what we were talking about because the average rate of change is f of 0 minus f of negative 5 over 0 minus negative 5. And finishing that up, or just hitting that up, that f of 0 is 2 minus f of negative 5 is 0 over 5. This just gives you 2/5. So right away, that's a very seemingly simplistic problem to talk about, but it's also one that is so easy to kind of miss because you don't know what you're doing. Then it says for -5 to c, let g be the function defined by this. So this is another example of our accumulation function. G is the integral of all this. And then it says to find the x-coordinate of each point of inflection of the graph of g. All right, so to find the point of inflection, we need to figure out first what g prime of x is. And g prime of x is equal to f of x. Second, we need to know that points of an inflection occur when g prime of x changes, changes from increasing to decreasing or decreasing to increasing. Because g double prime of x would be equal to f prime of x. And those are where points of inflection occur when g double prime of x changes sign. So looking back at this graph, this is the graph of f. And I can't see where g double prime or f prime of x changes sign, but I can see where it changes from increasing to decreasing or decreasing to increasing. I can see where this is happening. So if I look back up here, g prime, because this graph of f is equal to g prime of x, it's changing from decreasing to increasing right there. So I can say at x equals 3, x equals -3, f of x, which is equal to g prime of x, changes from decreasing to increasing. And then I can say at x equals 0, f of x, which is equal to g prime of x, changes from increasing to decreasing. So this one question ties in so much calculus in just a single question. It wants you to know that in this scale that we had of f, f prime, f double prime, that f being a concave up means that f prime is increasing and f double prime is positive, and f being concave down means that f prime is decreasing and f double prime is negative. Well, if I change between them, a point of inflection means I'm going from increasing to decreasing, and I'm going from positive to negative, or vice versa. So this is a chart that you really need to also have in your mind, because this question defined a function that was not part of the graph. It defined an accumulation function right here. And to answer the question about the point of inflection, you had to know how to take a derivative of the accumulation function. Okay, moving on. Then it says find the value of c for which the average value is 1/2. This is a question about average value. This actually goes back to what we just did in the last section. Average value over this is 1 over b minus a times the integral from -5 to c of f of x dx, or f of t dt. It doesn't matter which one we pick. I'm going to say f of x dx because I know I'm going to get rid of that in a second. And that is equal to 1/2. So it wants you to find that value, 1 over c plus 5 times, and the integral from -5 to c, I need to figure out what the integral from -5 to c is. So let's go back up here and get the values down of what these different areas are. This right here is a quarter circle with the center, it's a radius of 2. So pi times 2 squared is pi times 4. This has an area of pi. Then this has an area of 1. This should have an area of 2. And this should have an area of 1/2 base times height. That should have an area of c. So the integral from -5 to c of this would be equal to 2 plus c minus pi minus 1, or 1 plus c minus pi. So I would actually want to show that a little bit more down here, but we'll just put that this is, let's swing it back here. 1 plus c minus pi equals 1/2. And if I multiply both sides by a 2 times a c plus 5, I would get a 2 times 1 plus c minus pi equals, this would be times a c plus 5, or 4 plus 2c minus 2 pi is equal to c plus 5. Or if I subtracted a c from both sides, I get c is equal to 5 minus 4 plus 2 pi, or 1 plus 2 pi. So that's another question that tied an average value and tried to manipulate you into seeing, can you really evaluate the average value while also knowing how to find the area underneath the curves, while also knowing that that can be applied in here to get this value. So finally, it says assume c is greater than 3, and then this function is defined by h of x is equal to f of x over 2, and it wants h prime of c. Okay, not as hard as it looks. We know that h prime of x is equal to, chain rule, the derivative of this is 1/2 times the derivative of the outer would be f prime of x over 2. Then we substitute h prime of 6, which it's asking for, is equal to 1/2 times f prime of 6 over 2 is 3. Well, what is f prime of 3? Go back up here. F prime of 3, remember it says that c is greater than 3, so f prime of 3 is somewhere in here. That is the slope of this tangent line. Okay, that's all that is the slope of the tangent line. Well, the slope is down 2 and right c, it's negative 2 over c. So if you go back down to the problem itself, f prime of 3 is negative 2 over c, and I still have 1/2, and the answer it looking for is just negative 1 over c. So a big AP problem that ties in a lot of stuff we just did in the last two sections.